bit, so the third bit in each group of 4. Add that to our current result, double it, rinse and repeat. You do that 4 times, and now you've done a point multiplication. This seems really complicated, probably because most people can't read it, but once you get the slides, it'll probably make a little bit more sense. And although it seems really complicated and awkward way of doing point multiplication, it's actually very fast. Because what we're doing here is we're going to be adding W bits of what we're trying to multiply in each step. So with a point double, or the basic point multiplication algorithm, you're going to, sorry, I jumped ahead of myself there. Say we're doing a 192-bit ECC operation, a point multiplication. The basic algorithm for point multiplication would involve 192 point doubling operations and 96 point addition steps. Whereas if we use this fixed point with a 4-bit window, we're going to be doing 48 doubles and 48 adds. So we do half as many adds and a quarter as many doubles. So it's a pretty simple operation. And okay, so this table now, that's going to be taking up space. So people who work with embedded systems, we know that space is at a premium. You know, if you had 4K to implement ECC, usually that's pretty much all you have. And it turns out, though, even with small tables, you can make a lot of progress. So in this 4-bit window case, you have 16 values, and there's 16 points, obviously. So what is a point? Well, a point is just an x, y on the curve. It's 48 bytes for 192. So we have 16 times 48 bytes, which is less than a K. So with less than a K, we can get nearly 4 times the speed. Jump over that. You guys can ask me. So results. Everyone loves numbers. And I have graphs right after this. So with the basic algorithm, the sliding algorithm for P192, a point multiplication on an Opteron processor takes about 1.4 million cycles. A fixed-base approach, fixed-base approach with a 4-bit window takes 600K cycles. So we're nearly at a third there, and we're using less than 4 kilobytes of memory. It's pretty cool. Well, we're using 4 kilobytes of memory if you're using a standard math library. If you actually optimize it for size, you can get that way down. An 8-bit window gets us 400K cycles. A 12-bit window gets us 260K cycles, which is pretty insane if you think about it, because this means that on a high-end Opteron, you can be doing 10,000 point multiplications a second in software. That's the typical thing you'd only see in hardware with RSA. So you can get a lot of bang for your buck and avoid buying expensive hardware with that. So graphs. So that one, I don't know how much you guys can read it, but it's going through all the different NIST curves with different window sizes. So from left to right is 192-bit all the way to 520-bit. And in each group, it goes from a 4-bit window to a 12-bit window. So basically what you can take away from this, though, is that a 12-bit window will get you a very nice speed up. But unfortunately, next slide, the memory requirements for it are huge by comparison. So this is a graph. And the 12-bit window usually takes about a megabyte of memory. So your typical embedded device will not like that. There's kind of a happy medium, it turns out, with, at least on the Opteron, that an 8-bit window will give you average performance and average memory requirements. So quick wrap up. ECC is a fast way of doing public key crypto. Yeah, okay. Let me wrap up, please. It's a fast way of doing public key crypto. Super hard once you wrap your mind around working with points instead of scalars. There's patents you have to know about, like Apple has random patents on things. Toorcon has patents on things. RSA probably has patents on ECC. But for the most part, if you stick along the lines of using NIST or Suite B, you're pretty much safe. Yeah, I was listening. My Winamp jumped onto YouTube while I was writing these slides, okay? But the standards are kind of a mess, so it's good to get on top of it. The ANSI standards are what you'd want to be looking at, because that's what NIST defers to when they say, let's do DSS with ECC curves, ECC crypto. They're going to say use ECDSA or whatever else. Toorcon is really reaching, so don't do business with them. If anyone here from Toorcon, got to talk with you. Their standard tactic is, if anyone's been to ECCCon I think it's in Toronto, their standard tactic is just to scare people with saying, oh, we have all these patents and technology, and we're the gods with ECC. And the truth is no. I mean, I wrote this stuff for fun. Like, this is what I do after I come home from work. And I have, fast point multiplications, and this is used in real embedded systems and what have not. So why do you have to deal with Toorcon? It's beyond me. The Suite B stuff, ANSI stuff is home free. Fixed point is hella fast. If anyone wants to talk to me about it after the talk, I know that the slides weren't quite well prepared for this size room, but I'd be glad to explain it. The source code's there too, so libtomcrypt.com has these projects. code's public domain. It's well commented. And I also take bug fixes and stuff. So if you guys hack at it and find at least a dozen errors or so, give me a shout. And please stop using OpenSSL for generic crypto stuff. I hate seeing demos of crypto using OpenSSL. It's very annoying because that library is a pain to work with. And finally, questions, if anyone has any. Sure. Yeah. No, because the problem there is the table size grows way exceptionally large. It's linear increase in speed for exponential size and memory, so that's kind of a pain. You can play some tricks though. You can actually do some point compression on the points you have. For example, these are all going to be projective points, x, y, z, right? It turns out you can map it back to a fine and save one coordinate and stuff like that, but for the most part it's exponential. And you can see that here. I mean, the 12 size is huge. I mean, this is a log-log graph, right? So the top line's 1,000,000 and the bottom line's 10,000. So, any other questions? Oops. Buy my book. Yeah, sure, go for it, man. Rush job. I know, but if I went through the conclusion and all that stuff at my normal pace, it probably would have taken 10 minutes. And what? Yeah. Well, I didn't want to.
Unfortunately, something like this shouldn't be rushed.
Yeah, I hate John Callis.